Before we move on to the next little bit in section 4.4, let me just kind of go back and revisit the ending of the botched video where I dropped a sign. So we went through all of this work to find a differential operator that annihilates the function y equals 5 e to the negative x cosine of 2x minus 9 e to the negative x sine of 2x. And we saw, based upon the recommendation in the textbook, that the desired linear operator should be d squared plus 2d plus 5. And the claim was that this should annihilate the function y. I wanted to go ahead and verify that, but there was a sign mistake somewhere. If you can find it and link or email me the exact time and notation of what the mistake was, I'd be more than willing to give some bonus points towards your next test if you can find that error. But I went back and redid it, and sure enough, if you apply this linear operator to that function, it does annihilate it, and we will end up getting 0. The flow of the work, I tried to write the least amount as possible, which still ended up being quite a bit. But in particular, when you apply this differential operator, you're applying d squared to the function, the operator twice the derivative to the function, and then 5 times the original function. One of the things I did to kind of help condense on the writing is to get the second derivative, you at least have to do the first derivative. So I did the first derivative here, which was this part, and instead of having to recopy the whole thing and multiply by 2, what you should notice is that everything that's here in this one was me just combining the terms here and then mentally multiplying by 2 just to save some of the writing. So the workflow kind of looks like this. Get the first derivative here, so I still have one more derivative left to do. There are some like terms in here you can combine, and then this middle term is twice that derivative. Combine and multiply by 2 is how we're making the quick step to this part right here. You don't see the derivative being done a second time. But then take one more derivative after simplifying this piece. See, there it is. So there was that first derivative simplified. Doubled it, put it back here to make it simplified. Take one more derivative, combine like terms, and it is in fact true that it will be annihilated by that differential operator. So life is good, especially if you can do basic algebra and arithmetic. You can do differential equations. What we're going to look at next is just kind of highlight some of the properties we've already seen of differential operators. Let's suppose that L is an operator that annihilates both y1 and y2. So that means that if you apply the differential operator L to the function y1, we get 0. And if we apply L to y2, we also get 0. Then it will annihilate their linear combination, c1y1 plus c2y2. Where C1 and C2 are real numbers. So to kind of see what that would look like when we say that it annihilates it, so if we apply L to the linear combination C1y1 plus C2y2, because it's a linear operator, that's L of C1y1 plus L of C2y2. We can always factor constants out of differential operators. So that's C1 of L of y1 plus C2 of L of y2. And then remember, these two terms are 0. So we get 0 plus 0. So sure enough, L will annihilate their linear combination. The second thing that's very important in terms of properties is that linear differential operators commute. So if you applied the operator L1, L2, which would, remember, kind of like just like composition of functions, this would actually work from right to left. L2 in that form would actually be applied to the function first, and then L1 would be applied to the result. But the product operator L1, L2 will be the same as the product operator L2, L1. Okay. And then the next thing that's going to be very important for us is the following. Let's suppose that we have two differential operators, L1 and L2, such that L1 annihilates a function y1 and L2 annihilates a function y2. Then the product operator L1 and L times L2 will annihilate y1 plus y2. To see why that's true, let's go ahead and apply this product operator to the sum of these two functions. Or you could even do the linear combination with constants in front. But again, these are linear, so this would be L1 L2 of y1 plus L1 L2 of y2. Now remember, these things commute, so I can change the order here for the first part and call this L2 of L1 of Y1 plus here, because L2 annihilates Y2, this simply becomes L1 of 0. And that's just going to be 0. And here, now if we apply L1 to Y1, that becomes 0. And then L2 of 0 is going to give us 0 as well. So if you have two linear operators, L1 and L2 differential operators, that annihilate two functions, then the sum of those functions can be annihilated by the product operator. Okay. And now this brings us to the method of undetermined coefficients. How can we use this information to actually solve differential equations with constant coefficients? Okay. So again, we're going to be supposing in this situation that the g of x function we're working with is of the following family. It's a constant, or polynomials of degree 0, x to the m's times exponentials, x to the m's times e times cosines. Okay, and of course x to the m's times e times sines, where the alpha could be 0 here, so you could even get things like just x times sine, for example. But we saw earlier, and I linked this in the D2L, there's a handout that tells you exactly, okay, if this is the function of this form, then this is going to be the differential operator that will annihilate it. Okay, so if we can, as long as we can annihilate any one of these pieces individually, which we know how to do through the use of these three different styles of operators that we saw, then according to what we just saw in the last property, then we can annihilate any linear combination of them, any sum, by just simply taking products of these three styles of basic operators. Okay? So by solving the homogeneous higher order equation, L1 of L of y equals to 0, we can discover the form of a particular solution y sub p for the original non-homogeneous equation L of y equals to g of x, and then substitute this assumed solution into L of y equals to g of x to find a particular solution. This procedure is what we called the method of undetermined coefficients, and we're going to see this in the next example. Okay, so again, the basic idea is this: if we can find a function such that this function, differential operator L1, can annihilate g of x, then when we apply that L1 to both sides of our original differential equation, so starting with, here's what we're looking for. We have some function, some differential operator, let's call it L of y equals to g of x. That's how we're writing it now. And let's suppose that L1 is a differential operator that annihilates g. In other words, L1 of g of x equals to 0. Well, if that's the case, then when we apply L1 to this differential equation, what we get, this part is going to be 0, because remember, L1 annihilates g, and what we get is a resulting homogeneous differential equation. Okay? We know how to solve those from what we did before. A lot of times you can just work on the auxiliary equation, solve that, and then what we're going to do is we're going to substitute this assumed function form in to find the undetermined coefficients, to find the form of our particular solution y sub p. So that's the game plan. That's what we're going to do in the next example.